At the beginning of the 20th century, it became apparent that certain experimental observations were not able to be explained by the prevailing classical Newtonian physics of the time. It took the introduction of the quantum theory of matter to provide adequate explanations for phenomena such as the photoelectric effect, the Compton effect, blackbody radiation, and atomic spectra. In this video, we look specifically at atomic emission spectra as a way of explaining why the energy of electrons is quantized, and this is the first step in understanding the nature and structure of electron clouds, and more specifically the electronic structure of atoms. The cornerstone of quantum theory is that energy can only be transferred between systems or objects in discrete amounts. These discrete amounts or packets of energy are called quanta of energy, which is the plural. A single packet of energy is called a quantum of energy. In classical physics, and indeed in our everyday experience, it is thought that any object can attain any arbitrary energy value simply by transferring a sufficient amount of energy. It turns out that this is not the case. The energy that an object can attain is actually restricted to certain allowed energy levels, and the transfer of energy to increase or decrease the object's energy can only occur in discrete quantum leaps. In other words, energy is said to be quantized. And we can use the heating of matter to demonstrate this quantization of energy. When we heat the atoms within a solid metal to high enough temperatures, they emit white light. For example, consider the tungsten filament inside a light globe, which is heated by passing an electrical current through it. Such an emission is known as a continuous emission, since white light is actually made up of all the colors of the visible spectrum, and the visible spectrum is only a small part of the overall electromagnetic spectrum. When we heat the atoms of gases rather than solids, we see something quite different compared to the solid state. What we see is that the emission of light occurs in discrete, non-continuous bands of light at specific wavelengths. For example, the emission spectrum of hydrogen atoms in the gaseous state shows visible lines or bands at wavelengths around 656 nanometers in the red part of the visible spectrum, 486 nanometers in the blue-green part of the visible spectrum, 434 nanometers in the blue part of the visible spectrum, and 410 nanometers in the violet part of the visible spectrum. When we heat helium gas, we see similar discrete bands of light emitted, although the number and the positions of the bands are different and are specific and characteristic for each different element. To understand the implications of this type of line spectrum, we need to know a bit more about light in general, and we need to know that each of these lines or bands of light correspond to a particular wavelength and frequency of light. We can see that as the wavelength of light, or electromagnetic radiation in general, increases, the frequency decreases, and wavelength and frequency are inversely proportional according to this relationship here, where lambda refers to the wavelength of light, c refers to the speed of light, and u refers to the frequency of oscillation of the light wave, or more broadly, the electromagnetic wave in question. It is also important to note that each frequency or wavelength of light corresponds to a particular energy, described by the Planck-Einstein equation, which shows that the energy is directly proportional to the frequency via a proportionality constant called Planck's constant. In 1905, Albert Einstein was able to use this relationship to explain the photoelectric effect, which until then had escaped a satisfactory explanation by the prevailing classical physics at the time. The photoelectric effect involves shining light or electromagnetic radiation onto a surface, with the result being a release or emission of electrons. At the time, light was considered to be a wave. It could be reflected, refracted, diffracted, and it could set up interference patterns, all properties of waves. Einstein's intuitive leap, which won him the Nobel Prize some years later, was to consider that light can be shown to act as tiny packets of energy, and that this energy can be transferred to other objects or systems, such as electrons, to increase their energy. In the case of the photoelectric effect, the energy of electrons is raised to such an extent that they are driven from the surface of the material. These little packets of energy that make up light are now known as photons. And according to the Planck-Einstein equation, long wavelengths of light, or low frequency of light, correspond to low energy photons. And we find relatively low energy photons in red light, infrared radiation, microwave radiation, and radio waves. On the other hand, short wavelengths of light, or high frequencies of light, correspond to high energy photons, and we find relatively high energy photons in blue light, UV radiation, X-rays, and gamma rays. The atomic emission spectra of elements such as hydrogen and helium that we saw earlier involve understanding how light, or electromagnetic radiation in general, interacts with atoms. Atoms can absorb or emit energy in a number of ways. One important way involves electrons. An atom can increase its energy by increasing the energy of its electrons. For example, an electron in an electron cloud can be said to sit at a certain energy level, say E1, and it is able to transition to a higher energy level, E2, by absorbing energy in some way. Conversely, an atom can also lose energy by decreasing the energy of one or more electrons in its electron cloud. So how can electrons increase or decrease their energy? One way that electrons can increase their energy is by absorbing the energy of photons. The energy of a photon can be transferred to an electron to increase it from a lower energy level to a higher energy level, and in that process the photon is annihilated and ceases to exist. The magnitude of the energy increase depends on the energy or frequency of the incoming photon. High energy photons can cause a large increase in the energy of an electron, while lower energy photons will result in a smaller energy increase. Electrons can also decrease their energy by emitting photons of light. So an electron can transition to a lower energy level by releasing energy in the form of a photon. And the energy or frequency of the photon released is a measure of the decrease in energy of the electron. But, and as you can see, it's a big but, the light that we see in atomic emission spectra show only certain discrete and characteristic wavelengths or energies of light are emitted from atoms. In other words, it seems that only certain energies of light are allowed to be emitted from atoms. It therefore follows that only certain energy levels are allowed to exist within atoms. And so we come to one of the most important consequences of quantum theory, as well as one of the most important scientific discoveries of the 20th century. The energy of electrons within atoms is quantized. The electrons in atoms and molecules exist in definite, discrete, non-continuous energy bands, and therefore the energy an electron can attain is not arbitrary. It is, as I said, quantized. And the evidence for this lies in the observed atomic emission spectra of atoms and in other observed phenomena such as the photoelectric effect, the Compton effect, and blackbody radiation. If we want to draw an analogy with the electron energies in atoms, we can use a ladder as an example. A person can climb up and down a ladder, raising and lowering their energy by going from one rung to another. That person is allowed to step from any rung to any other rung, but cannot stand in the gap between the rungs. Similarly, an electron can jump from any allowed energy level to another allowed energy level, but it cannot exist in the gap between energy levels. To move from one energy level to another, an electron must gain or lose just the right amount of energy. Unlike the rungs of a ladder, however, the energy levels of an atom are not equally spaced. In fact, the energy levels get closer together at higher energy levels. So let's summarize some of the important characteristics of electrons in electron clouds within atoms. Electrons exist within atoms in discrete energy levels and cannot gain or lose any arbitrary amount of energy. They can only move between specific allowed energy levels if the exact amount of energy is supplied to or lost by the electron. In loose terms, electrons close to the nucleus have low energy, electrons well away from the nucleus have high energy. It is possible for these electrons to move between the discrete energy levels if the levels are not fully occupied. Electrons move to a higher energy level by absorbing energy in the form of photons. They move to a lower energy level by emitting energy as photons. The energy levels, and therefore the energy gaps, are fixed within a particular type of atom, but differ between different types of atoms. And this is why the emission spectra of different elements are different and unique to each element. In the following video, we will look specifically at the atomic emission spectra of the simplest atom, the hydrogen atom, in much more detail.